Okay, week 28, part 1, we're talking about lenses, convex and concave. So we've talked about mirrors for sure, and lenses look very similar. So we have, convex and concave. The main difference is that light bounces off, and this is going to seem straightforward, but it definitely plays a role in our understanding. So for mirrors, light bounces off them, and lenses, light passes through them. And other than that, they behave very similarly in terms of the equation to find distance to image and distance object and the array diagrams and that kind of thing. So before we get into lenses, let's talk about refraction again. We have talked about refraction previously. So this is waves, but more specifically because we're talking about light. So light bends as it passes from one medium to another. And I'm going to try to explain why that happens with this diagram here. So light bends as it passes from one medium to another, and if we just look at this, I know there's a lot of information there, but here, so we have something like air and something like water. And one specific light ray would be this. And so what happens as this ray of light comes in is it hits the surface, and then it's going to actually bend. It's going to change direction. And this one as well would change direction. So these can be thought of as wave fronts, like the up and the down and the up and the down and the up and the down. And what happens when light is going through air is it's going fast, 3 times 10 to the 8th meters per second, and it's going to actually slow down a little bit as it passes through water. So imagine that this is a line of people walking or something, and these people, as soon as they hit this water, they start moving slower, and these people move slower, and these people move slower. And so do you see how as a result of right here, because this stuff starts moving slower, the wave fronts get bunched together. And because they get bunched together, the direction in which those waves are traveling changes. So this is sort of a description of why light will bend as it passes from one medium into another if it goes different speeds. So let's say that's 3 times 10 to the 8th meters per second. In this medium, it might be something like 2.9 times 10 to the 8th meters per second. And what that would mean is that because it's going slower in the water, it's going to bend as it passes through. Okay, so brief explanation there of refraction and why it happens. There's a way that we can calculate, so this is called Snell's law, and here's the way it looks. N1, that's not an I, that's a 1, times sine theta equals N2 times sine theta 2. So I'll explain what this means. We have 2 different media here. So let's say we're talking about something going from air into glass. Where's the A? There we go, glass. Alright, so here's the boundary between those 2 mediums. Here's air over here, and here's glass over here. And the way this works is if the light, so there's our ray of light going from air and then into glass, and we describe this as the angle of incidence and this as the angle of refraction. Angle of refraction and angle of incidence. Incidence. I think that's how it's spelled. So incidence, that's where it comes in and hits, and then angle of refraction, that's as it's passing out into the other medium. N in the equation, so we'd have This is a specific index of refraction over here and a specific index of refraction over here. So this is a property of the medium, and we're going to talk about that on the next page, what that actually is. It has to do with how fast light goes through it. So this is an example, or that's the that is Snell's law, sorry, and we have an example down here. So the example says light in air is incident upon a piece of crown glass, so that's just a specific type of glass, at an angle of incidence of 45 degrees. What is the angle of refraction? So here's my diagram where here's the boundary between the two mediums. We have air and we have glass over here, and we're basically going to be using n equals 1, more specifically it's 1.0003 for air, and then for glass it's 1.52. So substituting in, this is what Snell's law looks like. So we're told that the ray of light hits here's the air-glass boundary at a 45-degree angle, and then it's going to bend. So this we would call the angle of incidence. We have that right here. And then this we'd call the angle of refraction. That's right here. And so our index of refraction for both sides, we have 1 for air and 1.52 for glass. So this side of the equation is for air, and this side of the equation is for glass. And solving down, we would divide both sides by 1.52. So plug that into your calculator, you get this, and that's equal to the sine of the angle. So we know we can take the inverse sine of this to end up with 27.7 degrees. So that would be this angle right here, angle of refraction. Okay, so what exactly is the, let's see, total internal reflection? No, we should be up here. All right, what is the index of refraction? Okay, index of refraction is a measure of how fast light goes through the medium. So how fast light goes through the medium. And we can say that n equals c over v. Let's see, does that make sense? Yeah, that makes total sense. So what we have here is that the speed of light through some medium is equal to c, where, what is the speed of light? Over here, we're talking about c being defined as 3 times 10 to the 8th meters per second. So this is actually the speed of light through empty space or through a vacuum. So v equals c over n. So this, when we say n is 1.5 for glass, it means we take 3 times 10 to the 8th and divide it by 1.5 to get the speed of light through that medium. Okay. So that's what that little n means in the equation. Total internal reflection happens, so you might want to draw this right there. Let's say we have water, and this is where we sort of see this most frequently. So there's something under the water that's emitting light, or light is bouncing off it, right? And as it passes through from water to air at different angles, so let's zoom this in a little bit. So if it's like this, it goes straight through. If it's like this, it bends like that. If it's like this, it bends like that. If it's like this, it bends like that. So we get to some spot where this right here, the light would actually be passing out into air perpendicular to the surface, which means it doesn't actually pass out into air. So this right here we call the critical angle. That's a critical angle, and it's sometimes called theta sub c. but that's the angle at which total internal reflection occurs. And so if you were solving, you could say that the angle of refraction for that is 90 degrees. So check these out. Let's get that stuck there so we can move this out of the way. So here is a picture from underwater, and you're seeing total internal reflection. So in this region, you actually see, so this is a picture taken from underwater, you can see out and you can see the sky, and there's these big fish in there. But once you get past a certain angle, all of this is light being reflected from the ocean off the surface of the water back to us. You can even see it looks like reflections of the fish. So an example of total internal reflection, and here's a little artsy photograph that's similar. So this is from the bottom of a pool, where these are the lap lanes, and those are probably those floaty things. Oh, maybe those are the lap lanes. Well, whatever. So here's underneath, and then this is all reflection of the stuff from underneath. Whereas this, we can see up through the water to the ceiling of the, looks like it's in some big stadium or something like that. So two examples of total internal reflection. And notice how, so if we were looking from down here, this, we'd actually be able to see light coming in from above. Whereas when we looked out here, all we would see is light being bounced from the bottom of the pool or ocean or whatever. Okay, so we're going to get into lenses, very similar to mirrors. Take a look at the thin lens equation, or lens maker's equation, this is sometimes called. So we used this for mirrors, and it's exactly the same. Distance to the image, distance to the object, and focal length. Magnification, same thing. Ray diagram is very, very similar, except that, so over here you could just write that these are the same. If you don't know what these are, you should look it up and then define all those variables. So I did just say that magnification, height of image, height of object, distance to image, distance to object. And over here, so a ray diagram, this would be our image, and we would have a ray of light that comes in parallel and then passes out through the focal point. So notice how this is a lens, light is passing through it. And then a ray of light that passes through the focal point is going to pass out parallel. And of course, where those cross, that's going to be the image. And this was the object. Okay. Over here, this will always be where the object is, and that's positive. And because we expect light to pass through, the distance to the image on this side is positive as well. So that's the only difference right here, in that when light actually passes through and ends up over here, we say that the distance to the image is positive. Okay, that's it for lenses and refraction.